chapter 5 today. And chapter 5 covers chemical reactions and chemical equations. And we're going to kind of start off with some of the basics in terms of how do we know that a chemical reaction is taking place versus a physical change. And then we'll move on from there to actually getting into the writing of chemical equations, the balancing of chemical equations, and then probably the most difficult task, which is identifying chemical equations by their type, which is a task that requires a little bit of practice. But once we understand that particular practice, it actually goes a long way to helping us balance equations faster and more accurately than we would have been able to do before. So let's get into the material itself here. First and foremost, got to ask the question, what is a chemical reaction? If we're going to try to identify chemical reactions, we need to identify what makes a chemical change a chemical change. And at the simplest kind of explanation, what we are talking about is interconversion. We're talking about the change in the chemical composition of substances as a chemical change is occurring. And so from the standpoint of a chemical reaction, we can break a chemical reaction up into two categories, two groups. There are the reactants. That is, there are the substances that are ultimately participating in the chemical reaction that are going to undergo the chemical change and are going to convert into some new kind of compound or element. And then we have the products. The products are the result of the chemical reaction, the chemical substances that form as the result of the chemical change. The only difference between the two is a literal reconfiguring of the reactants to make the products. This speaks to a larger concept the law of conservation of matter, which says that atoms, matter, can't be created or destroyed in the process. So every single atom that was there present as reactant is there present as product. The only difference is how those atoms are arranged with each other. In the reactants, we'll have a group of substances that are combined in one way. In the product, we'll have them combined together in a different way. But nonetheless, those atoms that make up those compounds did not change. All they did was attach and reattach to different elements, different atoms along the way. How do we know a chemical reaction has taken place? Well, there are usually some telltale markers. So take, for example, this three-panel diagram here. Here I've got two clear, colorless liquids separated in beakers. And here I have combined the two together, and it's hard to see, but in this third panel, what we have is we have some bubbling taking place in this third panel in the larger beaker. That's one of the telltale signs. So how do we know that we have a reaction occurring? What are some ways that we can tell that something's going on? Well, these pictures give us some kind of clue. What are some things that are happening in these pictures to let us know that these are chemical changes rather than just simply physical changes? So what do you see here? What are some things that jump out as this is happening and it's letting me know that there's a chemical process going on? All right, good. Color changes. We're seeing color changes in A, in D, in B in particular. Well, we can even make an argument that we're seeing a color change in F as well. None of the substances that were brought together in the Bunsen burner were ever blue, and yet we have a blue product of that reaction in the form of the flame. What are some other things that we can look at that indicate a reaction might have occurred? Okay. Okay. We see the formation of a gas in D. We see the formation of a gas in H. Anywhere else where we see gas forming? Right. Okay, David's pointed out temperature change. And that's being pointed out to us in B. The magnesium strip has caught on fire. In C, the thermometer has indicated that we are dropping in temperature. We can also see that F has an implied temperature change because of the heat. That's probably about as far as we can take it. Formation of a solid, another good one. A is an example of a solid. B, the smoke that you see is actually a solid being formed as that magnesium is burning. E has that. G has that as well. So these are all good kinds of clues. And a more comprehensive list can be found here. Some of the most common observations that we can notify: changes in color, which we mentioned, production of light. So we're talking about the spontaneous production of light. If we have some kind of process occurring and it's giving us light as a result, there we have our evidence of a chemical reaction. The formation of a solid. So if I put two liquids together and a solid forms, or in the case of the magnesium, we saw that smoke, that particulate nature of that gas, the solid part of that is a sign of a solid forming. Metal coating. Formation of a gas. I see bubbles forming in a solution. Or I notice that a particular reaction is giving off some kind of a vapor that smells. Usually smells bad. That's kind of how we recognize that it's there. And then finally, changes in temperature. absorption of heat, release of heat. Sometimes that release of heat comes in the form of a flame. Sometimes it just happens to feel really hot. We saw in window C here, this particular substance was dropping in temperature as it reacted. So temperature changes can be positive or negative, but either way, they tend to indicate that a chemical reaction has occurred. Now, ordinarily, we'll see multiples of these. We won't just see one of them. We'll usually see more than one of these. So of these, temperature is probably the most confusing because a lot of physical processes come with temperature changes as well. You know, if you melt ice, you're going to see the ice change in temperature from 0 degrees Celsius to eventually room temperature as it melts and reforms. So we do have to be a little bit careful of that. What we're really talking about there are spontaneous kinds of processes. As we see the reaction occurring, we see a change in temperature occurring with it. And so we come now to talking about chemical reactions and chemical equations. And a chemical equation is a symbolic representation of a chemical reaction. Ultimately, it shows a couple of things. First of all, it gives us the chemical formulas for the reactants and the products. A proper chemical equation also tells us in what phase of matter those reactants and products exist. And so, just as a little key here, S refers to something in the solid state, L refers to something in the liquid state, G refers to something in the gas state, and AQ refers to something in an aqueous form. Does anybody remember what aqueous means? I'm sorry? Dissolved in water, that's right. So a chemical equation shows us the reactants, the products, and their phases of matter. What it also shows us is the relative numbers of each kind of reactant that form, that combine, and the relative amounts of product that form. We do this through the balancing of equations. Proper equations can also give us special conditions. So what kinds of things mightn't be necessary for the reaction to occur? Things like constant heating or electrical current. And we usually see those in the forms of symbols. If you see the triangle symbol, that's the Greek letter delta. That indicates that we are heating something continuously to get it to react. If we see ELEC or ELE, that means that requires an electrical current to run through it. We saw an example of this in lab. If you remember from the, which lab was that? It's one of the early ones. The Hoffman apparatus. We had the machine that was hooked up to the battery that separated the hydrogen and the oxygen from it. If we were to write that chemical equation, we would in order for it to be complete, we would include ELEC because we had to run that reaction by shocking it with electrical current. Simply heating the water was not going to get it to split into hydrogen and oxygen. We had to provide a significant amount of energy through electricity. When it comes to chemical reactions, let's take a look at this panel here. We can see that the reaction between hydrogen and oxygen is an explosive one that produces water molecules as a result. The question here is, do we conserve mass? So if I look at the panels, what I need to observe is how many of each atom are present in the reactants versus in the products. So if I'm counting up oxygens, I have 3 oxygen molecules. Each molecule has 2 oxygen atoms in it. So I have a total of 6 oxygens in the reactants. And if I look at the hydrogens, I have 6 hydrogen molecules, 12 hydrogen atoms in total. On the product side, I have 1, 2, 3, 4, 5, 6 H2Os, which would give me 6 oxygen and 6 times 2 for 12 hydrogen. So I can see that in this chemical reaction, my atoms are conserved, which means my mass would be conserved as well. Now, this particular principle, the law of conservation of mass, is very closely related to the law of conservation of matter that we discussed in the previous slide. All it is quantifying it into something that we can measure on a balance, as opposed to something that we have to count from a molecular standpoint. But it brings us to a really important observation of chemical reactions. And that is that chemical reactions obey these laws of conservation. How do we represent that law of conservation in a chemical equation kind of form? Well, that comes when we do something called balancing. Balancing equations is based upon something known broadly as the law of conservation of matter. The law of conservation of matter states very definitively that in any chemical process, matter cannot be created or destroyed. Every atom of every reactant present at the beginning of the chemical reaction is also present at the end of the chemical reaction as well. Every atom in the reactants becomes part of the products. So when it comes to balancing chemical equations, what I have to make sure I do is account for that principle. So let's take this chemical reaction in question here. This is called the thermite reaction. The thermite reaction, we have a powdered mixture of aluminum and iron 3 oxide heated together. The reaction is quite exothermic, generates tons of heat. And the end result is that we get molten iron along with aluminum oxide. This particular reaction is very common in certain industries. Probably the most common application of this is in the railroad industry. If a railroad track develops a crack or otherwise is impassable in a place, the thermite reaction is used to generate molten iron to fill in the gap to repair the railroad track. But if I look at it from this standpoint, I can see that I am not obeying the law of conservation of mass. After all, I can see that my reactant had 2 iron atoms, but there's only 1 iron atom here. And I only started with 1 aluminum atom here, but yet there are 2 in the product. And so our conclusion here is that this reaction equation that we've been given does not obey the law of conservation. The way to fix it is to balance the equation to get it to obey that law of conservation. Now, the next slide kind of goes through that same idea in a different way. Here we're showing atomically that there is an imbalance. 1 aluminum atom versus 2 over here. 2 iron atoms in the reactants compared to 1 here. So we've kind of answered these questions already. Is the equation balanced? Obviously not. We have different amounts of different elements on both sides of the equation. What has to change? We got to balance it. How do we balance it? Good question. We balance our equations using coefficients. That is, numbers on the outside of the chemical formula in this space here. Why coefficients? Why not subscripts? Why can't I just do something like this? I need 2 aluminums here. I'm just going to put a 2 there. I need 2 irons here. I'm just going to put a 2 there. Why can't I do that? Because we have to remember what a chemical formula is. A chemical formula tells us the exact identity of the substance in question. How many atoms there are, what the relationship between one element and another is in the compound. If I start playing around with subscripts to get things to match up, I change the identities. Now, in this case, it seems like somewhat of a moot point. Okay, what's the difference between 2 aluminums and 2 irons? But what if, in order to get it to work, I wanted to do something like this, where I said, okay, I'm going to change my iron. I only have 1 over here. Let's just change this formula to FeO3. And let's just change aluminum to Al1O3. Well, by the same logic, I could do that. Why can't I do that? Because this compound has a particular meaning to it. This means that I have iron 3 ions and oxide ions together. And I had aluminum ions and oxide ions in the other. To get it to charge balance, I have to have that particular formula. I start messing around with the formulas. I start messing around with the chemical composition. I don't want to do that. So what do I do instead? I balance with the coefficients. Balancing with coefficients, not too terribly difficult. Since I need 2 aluminums in this compound, I'm going to pull that 2 to the outside. Since I need 2 irons in this compound, that means I'm going to get 2 iron atoms on the flip side. So coefficients are the way that we do this and that we do it correctly. Can't monkey around with the subscripts, because changing the subscripts are going to change the identity of the substance itself. I have to use coefficients. By using coefficients, I can now express how I get the 2 aluminum atoms to make aluminum oxide, and I can express what happens to the iron in the iron oxide when it becomes molten iron, the product. From a balance standpoint, I now see I have 2 aluminums on each side, 2 irons on each side, 3 oxygens on both sides. I now have a balanced chemical equation. Every atom is accounted for. The equation now follows the law of conservation. And that's what we want ultimately. So how do we get to this spot? If I give you a random equation, how do I know what to do? Well, luckily there are some procedural steps that can help us to figure out how to balance equations and how to balance them appropriately. What I advocate for is something I call the atom economy method. The atom economy method is very similar, but less pictorially taxing to what the book did here in kind of monitoring the number of atoms. So instead of doing all the drawings here, I'm going to do a register of how many of each atom are on each side of the equation. So what the book did is essentially what I'm going to do. Here are all of the elements in the reactants. Here are all of the elements in the products. I've got 2 of those, 3 of those, 7 of those, and on this side, I've got however many there are. As I change coefficients, I'm going to change my atom counts as well. And when I get to that spot where everything's equal on both sides, I know the equation is going to be balanced as a whole. Now, this process on its own can be somewhat tedious to do, but it's probably the best way, at least as you're learning kind of some of the tips and tricks, to make sure that you're on the right track. Now, in addition to these 3 steps, let me share with you also a couple of tips that I've come up with over the years to help make the process a little bit smoother. First tip, hydrogen and oxygen are very, very, very common elements. They tend to appear in a lot of different products, a lot of different reactants. Oxygen is especially notorious for this. Lots of compounds have oxygen in them. Easiest way to deal with something that's complicated is to basically avoid it. Leave the oxygens for last, because usually what happens is if you balance everything else first, by the time you get to oxygen, you'll have one more thing to balance. You'll have one more reactant or product to balance with. And the math will kind of work out where it's pretty easy to see what you need to do. So instead of going, okay, oxygen's out of balance, I'm going to do this. Oh, well, that affected the chromium. Okay, let's fix the chromium. Oh, the oxygen's out of balance again. Oh, let's fix the nitrogen. Oh, that put the oxygen out of balance again. Don't worry about the oxygen. Don't worry about the hydrogen until it's absolutely necessary. Then hopefully the math kind of works out and you can kind of figure out what you need to do next. Second tip, cluster groups of atoms together. In particular, what I'm talking about here are your polyatomic ions. In most chemical reactions, polyatomic ions stay together. There's probably one exception, decomposition reactions, where they don't. But for the most part, they do. So if you notice that you've got nitrate ion on the reactant side and nitrate ion on the product side, keep them together as a cluster. Track the number of NO3s as opposed to the number of nitrogens and the number of oxygens. Doing it this way will also make the task of keeping track of hydrogen and oxygen a lot easier, because some of your oxygens will be contained inside of those clusters. And it's a lot easier to maintain control and tracking of a cluster of atoms than it is individual atoms. So let's do some examples. Here I have the reaction between an iron oxide compound and hydrogen to make iron and water. So my first step is to set up my atom economy. I'm going to draw a line between the reactants and products, and I'm just going to monitor how many of each type of atom there are on each side of the equation. So on the reactant side, I have 3 irons, 4 oxygens, and 2 hydrogens. On the product side, I have 1 iron, 1 oxygen, and 2 hydrogens. Keeping in line with our tips and tricks, hydrogen and oxygen we're going to save for last. Let's worry about balancing the iron. Balancing the iron, very similar to our first introduction example. We're just going to put a coefficient of 3 in front of the iron, and I now have 3 iron atoms. Okay, thing to remember about the coefficients, they're multipliers. They multiply by everything that is in the substance that they're out in front of. So in this case, I had 1 iron atom. I put a 3 in front. That made it 3 times 1, 3 iron atoms. So I've got the iron balanced. Right now I've got hydrogen balanced as well. The only thing that's not balanced is oxygen. Now the only source of oxygen in this entire product side are in water molecules. How many water molecules do I need to give me 4 oxygens in total? 4. Each water molecule has 1 oxygen atom in it. 4 water molecules would give me 4 times 1, 4 oxygen atoms in total. Now, fixing this has left me with another hole. I didn't just change the amount of oxygen, I also changed the amount of hydrogen. 4 water molecules would have 4 times 2, 8 hydrogen atoms in total. So while I have fixed oxygen and iron, I now have a gap in my hydrogen. I need to balance hydrogen. Each hydrogen molecule has 2 atoms of hydrogen. I need 8 in total. 4 times 2 would give me those 8. And so that is my balanced equation overall here. Now, one other tip that I can give you that does tend to help often here, if one of my substances has multiple subscripts, one of the things that I can do to kind of expedite the process, make it a little bit faster, is oftentimes those subscripts end up showing up as coefficients on the other side of the equation. This example was no different in that regard. We saw it happen here as well. This isn't always the case, but oftentimes it is a good starting point to kind of help you to get to where you need to go. And so if you had done that from the start, you would have balanced the iron and the oxygen immediately and would have recognized that the hydrogen was out of balance and figured out what to do with the hydrogen next. All right, any questions with this example? Okay, so we're kind of running up against time here. So I'm gonna stop here for today. On Friday, we're gonna do more with balancing equations. We're also gonna introduce you to the 5 different types of chemical reactions. And the real nice thing about those 5 types of reactions, if you can identify a reaction as being in one of those categories, it actually does help with the balancing because there are certain characteristics that show up, especially in replacement reactions, that if you recognize, hey, I've got a replacement reaction here, you can balance it very quickly by recognizing what it is. So we'll leave that there for now. Don't forget about your homework assignment. Again, tomorrow night by midnight in Connect. That'll get you through the homework. You've also got proficiency and chapter 4 quiz to concern yourself with as well. Have a good afternoon.